Given the root of a binary tree, we must return its maximum depth, where the maximum depth is the number of nodes along the longest path from the root node down to the farthest leaf node. For example, in this tree, this is the longest path, which consists of 3 nodes, so the max depth is 3. Now, the way we're going to solve this is by using recursion. Here's a quick overview of recursion if you're unfamiliar. Let's say you were given a list of items, and you were asked to find the length of this list. Well, you can see that there is at least one item at the beginning, so you could recursively define the length of this list by saying it's 1 plus the length of the rest of the list. This begs the question, well, what's the length of the rest of the list? And we can find this by using the same recursive definition. Again, we can see that there is at least one item at the beginning, so the length of this list is 1 plus the length of the rest of this list. And it keeps going. The length of this list is 1 plus the length of the rest, and the length of that list is again 1 plus the length of the rest. But now we hit something different. We see that the rest of the list is now empty. This means that we've hit the base case, so we know that there are 0 items in the rest of the list. So now we're done with the recursion, and we can finally figure out the length of the entire list, which is 0 plus 1 plus 1 plus 1 plus 1, which equals 4. Now, of course, practically speaking, it would be much easier to just loop through the list and count it iteratively. But as you'll see in a second, when working with more complex data structures such as trees and graphs, solving things recursively can result in much cleaner and more concise code. Now let's look at the code and solve this in Python. Let's use the same tree as before, and we'll also be using this definition of a tree node here. Each node has 3 attributes: val, which is the value you see inside each node, left, which is a pointer to the left child node, and right, a pointer to the right child node. If either pointer points to none, then that means that there is nothing there, and we don't count that as a node. We start by passing in the root node of the tree into the function, which is this node in blue. Our base case will be if the node is equal to none, because that means we've reached the end of a path and there is nothing left to traverse. So in that case, since there are no more nodes to count, we can just return 0. Right now, the root node does not equal none, so we'll start the recursive cases. First, we'll find the maximum depth of the left branch of this node by recursively calling the maxDepth function and passing in root.left, which is a pointer to the left node. A small note here. If you're doing this inside of the LeetCode environment, since LeetCode forces your solution to be part of a class, this function call will have to be self.maxDepth. But for now, I'll be sticking to the more general solution. So at this point, we're going to call maxDepth and pass in root.left, the left node. I'm going to pin a blue dot here to show that this is where we left off in the function where the blue node is the root. So let's enter this new function, and now this green node is the root. We'll check for the base case again, which is still false, so we enter another recursive call to find the max depth of the left branch of this node. So again, we call maxDepth and pass in the left node. And this time, I'll leave a green dot to match the color of the green node. But now notice that root.left is actually none. So when we enter the newly called function, root is now equal to none. We finally hit a base case, and since we know that there aren't any nodes at this level, we can return 0 and go back up the tree. So we're going to exit this function and return to the function where the green node is the root. So now that we're back, I'll remove the green dot. We return 0, so the variable leftDepth is assigned a value of 0, which I'll indicate directly on the tree here. Now that we're done traversing the leftmost branch, we can move on and find the max depth of the right branch. And we'll do this the exact same way by recursively calling maxDepth, but this time pass in root.right. But notice that root.right is also none. So when we enter this function, the base case is true again and we'll return 0. We return to the function where the green dot is the root, and now the variable rightDepth is assigned a value of 0, which again I'll indicate here. We're finally done traversing both branches of the green node, so we can finally return the maximum depth that was found. In this case, both the left and right depth were 0, so the max of both of them is still 0. But since we also need to count the node that we're currently on, we're going to return 1 plus 0. We're now going to return to the function where the blue node is the root, and we'll pick up right here where we left off. We returned 1, so the left depth variable is now 1. As you can see, We finished exploring all the nodes in the left branch of the root, and we know that the maximum depth on that side is 1. So now it's time to explore all the nodes in the right branch. So let's do the same thing and recursively call max depth with root.right. So now the root is the node in orange. It is not equal to none, so we do another recursive call with root.left, which is the node in purple. This is still not equal to none, so we have to go down another level and pass in root.left. But now we finally reached the end, and the root is equal to none. So we'll return 0, and we know that the left depth of the purple node is 0. And we'll do the same thing for root.right, which is, again, none. So we return 0, and the right depth is set to 0. Then let's propagate back up to the orange node by returning 1 plus 0, which is 1. We're now back in the orange node, and the left depth is set to 1. Now we have to finish exploring the right side, and again, root.right is none. So we enter the function, hit the base case, and return 0. So now back in the orange node, the right depth is 0. The max of 0 and 1 is 1, so we're going to return 1 plus 1, which is 2. We've now finally returned back to the blue node, and we're going to set the right depth equal to 2. Now this is going to be the final return statement. The maximum of 1 and 2 is 2, and so including the blue node, the maximum depth of the entire binary tree is 1 plus 2, which is 3. So we return 3, and we are done.